Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashiru Mamboro. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. Welcome. As I said, today we'll be focusing on wave, sound, and light. Focus on Doppler effect. Now, if we check, Doppler effect is part of paper 1. According to the weighting there, you can see it has 15 marks. So we're looking at wave, sound, and light with 15 marks out of the 150, and that is 10% of the paper. So that is what we'll be focusing on, and I'm hoping that this is one of the sections where you can collect all the 15 marks. Then you have 10% for paper 1. Now, if we look at the structure of paper 1, you have a multiple choice question, which is section A with 20 marks, section B with 130 marks, which is your structured questions. The total is 150 marks for 3 hours. Now, as we always do, we always start with the exam guideline. We're saying everything must come from exam guideline. So ensure that as you are doing your definition, you only utilize the exam guideline. You don't write definitions that you get from other sources. Let's focus on the ones on the exam guideline. Now, if we look, it's saying Doppler effect with sound and ultrasound. The first thing there is that you must be able to define Doppler effect. And it's saying you must define Doppler effect as the change in frequency. So it's the change in frequency or pitch of sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. You will see as we continue, you will have to remember this definition because it's going to help you as you move with this section. Bullet number 2, it says you must be able to explain using appropriate illustration the change in pitch observed when a source moves towards or away from a listener. So we'll be talking about different scenarios where the source is moving towards or away from the listener. And then you must be able to solve problems using the Doppler equation. Doppler equation is given by FL, which is V plus or minus VL over V plus or minus Vs multiplied by Fs, which is the frequency of the source. We're going to unpack this Doppler equation so that you understand it when either the source or the listener is moving. So one must be moving. Either the source will be moving or the listener will be moving. You must be able to state the application. So you must know the application where we utilize Doppler effect. And then you must be able to do Doppler effect with light. When it comes to light, we're going to focus only on redshift, which is in the universe. So I say you must be able to explain redshift at the end of this lesson. You must be able to use Doppler effect to explain why we conclude that the universe is expanding. So all this is important for you to remember and to be able to know. So if you check this topic, we have 6 bullets there that you must know all of them before you go and sit for your exams as we prepare for the mid-year exams as well. Now, let's look at prior knowledge to say in grade 10, you have done wave, sound, and light. You have done sound as well. We said sound is an example of a longitudinal wave. So you have done that sound travels faster in solids than in liquids. So for example, here we have given you to show that when sound travels in water, it moves with a speed of 1,500 meters per second. But when it's traveling in air, it's 340. You will see this value of 340. We'll be using it most of the time. And then sometimes we'll say 341, 342, 343, depending on the question. But it will be around the value of 340 because when sound travels in air, it travels with that speed. In a still, we're saying sound travels with a speed of 5,900 meters per second. So you can see that when you have a solid substance, then sound is able to travel with a high speed. Now you have done as well the wave equation, which is V equals to F lambda. Remember, you must not confuse it with C equals to F lambda because C equals to F lambda. Here we're talking about the speed of light, which is your C, but now the speed of sound now is V there, which I indicated that depending on the medium of propagation, if it's in water, it will be 1,005. If it's in air, it will be 340. In a still, it will be 5,900. So you have to remember all that. The other thing that is very much important about this equation, the wave equation, is the relationship between wavelength and frequency, because you can make frequency subject of the formula, then you will have frequency equals to V over lambda. So you can see the relationship between frequency and wavelength to say as the wavelength increase, the frequency decrease. So they are inversely or indirectly proportional to one another. So this is what we'll be using to say as the wavelength increases, what is happening to the frequency. So don't forget that. And we are saying that frequency is directly proportional to pitch. So if frequency is high, it means we'll have a high pitch as well. So you have to understand this is the language that we're going to be utilizing as far as we're dealing with this topic of Doppler effect. Now let's go and look at the equation of Doppler effect equation itself. Remember we said it's Fl, we stand for the frequency of the listener. Remember, frequency is measured in hertz. So don't forget that. We have frequency and frequency is measured in hertz. And then we're saying the frequency of the listener is equals to, we open the bracket, we're saying V stands for the speed of sound in air, which is measured in meters per second. Remember, our velocity or our speed is measured in meters per second. We're having a plus or minus. We're going to explain that because here we've combined all the scenarios together. 4 scenarios have been combined. I will be explaining so that you know when do we use a plus on the numerator, the minus on the denominator, when do you use a minus or a plus on the numerator and denominator. Now, the Fs there stands for frequency of the source. And then we have the speed of the listener, which is VL, the speed of the source, which is Vs. So the one that we talked about, which is speed of sound in air, is the V. That has no subscript. So if it is a subscript, you look. If it's VL, the L stands for the speed of the listener. If it's Vs, it's speed of the source. So in equation, you will always have this information. You have to do your data collection so that you check which information you are given, so that you are able to choose which whether you're going to use plus or minus, as I will be indicating in the slides that comes after this one. Now we continue with the Doppler effect equation. We are saying there is a combination of 4 scenarios. So we're going to unpack them now to say scenario number 1 is when a moving source is approaching a stationary listener. If you look at these 4 scenarios, you will see that it's either the source or the listener will be stationary, the other one will be moving. If all of them are not moving, we want to have Doppler effect. For us to have Doppler effect, there must be movement of either the source or the listener relative to one another. Now, we're saying when you have a moving source approaching a stationary listener, we have a moving source moving away from a stationary listener. We have a moving listener. When the listener is the one moving, the source will be stationary. When you are the same, and then it's either it's approaching or towards. So it's either it's approaching or going away, moving away from the source. When it's a listener moving, then we talk to that one. So we're going to indicate when do you use the positive, when do you use the negative. Remember, if we're talking about sound, and then if a source, we're having a source that is going towards the listener, obviously what is happening is that the wavelength, which is the distance here between the source and the listener, will decrease. And remember, we said in terms of the relationship, to say as the wavelength decreases, the frequency increases. And as the frequency increases, we said the pitch increases. Remember, we said pitch and frequency are directly proportional to one another. So the main thing that we are going to look at is those 3 things to say what is happening to the wavelength. And if the wavelength is increasing, it means the frequency is decreasing. So all the time, you will look at the relationship between the wavelength and the frequency. And then we are saying whatever happens to the frequency, the same will happen to the pitch. So that's how we'll be moving. Now, if we're having a moving source of sound, so if the source of sound is the one that is moving, that will mean that now remember in our equation, we had a plus or minus here, plus or minus VL here. It was plus or minus VL, but now because the listener is stationary, when is the source moving, it means the listener is not moving. So it's 0 meters per second, the speed of the listener. So hence we'll write 0 there. Then our equation will have V over V minus Vs, which times Fs. So you see that if it's the listener that is stationary, VL becomes 0. Then you are remaining with V. But now, because this is up towards, moving towards, or approaching, when it approach, if I'm approaching you, obviously you will hear more. There will be high pitch, which means there will be high frequency of the listener. So what happens is that now you must divide by, there must be a negative in the denominator there. So whether it's going to be plus or minus depends whether it's moving towards or away. So what am I saying? I'm saying if the source is moving towards the listener, we're going to have the listener, this listener velocity, which is 0. but the speed of the source will have it. So we'll put a negative sign there. So I think you get that the formula changes. But at the end of the day, we are saying always write the formula as it appears in the data sheet. That is the first thing that we must emphasize. You copy the formula the way it appears on the data sheet. You check whether it's the source moving or the listener moving. Remember, we're saying if the source is moving, it will mean that the listener is stationary. So what you're going to look at all times, if I can go back to our formula there, at all times, you are checking which one is moving. So we're saying if the listener, the VL is 0, it means that the listener is stationary. And then VS won't be 0, because if both of them are 0, there will be no Doppler effect. Remember, we're saying for Doppler effect to occur, we're saying one between the listener and the source. There must be movement, so that there must be change in wavelength, there must be change in frequency. So hence we're saying if the listener is stationary, it will mean that the VL there becomes 0. Hence our equation now will have V divided by, but because it's approaching, it's going towards, we want the denominator to be small so that we can hear more frequency. The listener can get more frequency. Hence, we are saying it will be V minus Vs. So understand that we use the plus over minus, plus for the numerator and minus for the denominator when it's approaching. So when there is approaching, we will say V plus VL over V minus Vs times Fs. So understand that the plus there is when it's approaching, we want the numerator to be bigger. This one must be bigger so that the frequency of the listener can be bigger. Then the denominator, we must divide with a small number. Hence, it must be V minus Vs. So we are saying all the time when it's approaching, it will be V plus over minus. So plus over minus means it's approaching. When it's approaching, you use plus for the numerator, minus for the denominator. So don't forget that, because you will lose marks if you can make a mistakes in terms of those signs. So I want to emphasize that. Then when it's moving away, we want the denominator to be bigger. So when it's away, you will see if the source is moving away, or the listener will say V away. Then we're saying this must be small, V minus over VL over V plus over Vs. So for away is minus over plus. For towards is plus over minus. So don't forget that on this equation to say when do I use positive, because we have two options. It's either to be plus VL or minus VL. So we're saying approaching, it will be plus over minus. Approaching or moving away, it will be minus over plus, because we want the denominator to be greater than the numerator. I think you got that, so that when we start doing questions, you are able to utilize that information. Now, it can be a moving, if it's a moving listener, it will mean that the source is stationary, hence you can write 0. But remember, I emphasize that always let's start by writing the formula as it appears on the data sheet. So don't just start by writing this one. It's better to always just go to the data sheet and copy the formula, because already where you are seated, you have 1 mark of writing that formula straight from the data sheet. So we're saying go and copy the formula from data sheet, check which one is moving between the listener and the source. In this case, we have a moving listener, which means we have a source that is stationary. Then Vs will be equal to 0. Hence, we didn't indicate Vs at the bottom there. So you see it's V plus VL over V. So the denominator is becoming small. Hence, the frequency will increase because it's moving towards. But when it's moving away, still it will be minor, so that the numerator becomes small, so that the FL as well will decrease. So you have to understand that one to say for towards is plus, for plus over minus, for away is minus over plus. Then you always write 0 for the one that is stationary. Now let's look at the applications where you can see that beautiful picture there. It describes application of the Doppler effect with ultrasound in medicine to measure the blood flow of the heart of a fetus in the womb. So you can see that Doppler effect, we're using it in our medical field, and it's important that we understand it. And according to definition, we said Doppler effect is the change in frequency. It's the change in frequency of sound detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. I want you to have that one and understand that one, to say you must at all time know that this is a change in frequency of sound. Change in frequency of sound detected by the listener, because the sound source and the listener have different velocity. So we're saying if the velocity of the source and the listener are equal, we won't have Doppler effect. Remember, as I was explaining, I said there must be change in the wavelength so that there is change in frequency, and change in frequency means change in the pitch. So it's very much important for you to understand that definition, to say there must be change for Doppler effect to occur. There must be change in frequency of the sound that is detected by a listener, because of the sound source and the listener having different velocities relative to the medium of sound propagation. The medium of sound propagation that we're talking about, I've shown you that when it's in water, it's 1,500. When it's in air, it's 340. So you're able to see that this speed, the speed of this sound, it will depend. It will depend on the medium of sound propagation. And we are saying when the source of sound is moving towards the listener, the pitch sounds higher. Remember, we said when you say pitch, you must think about frequency. So I'm going to show you in the next slide to show you how the wavelength decreases as we move towards, how the wavelength increases as we move away from the source. And then we're saying when the source moves away from the listener, the pitch sounds lower. Remember, at all times, where you see pitch, just put frequency there. Where you see frequency, just put pitch, so that you know that when the same thing you are saying about pitch is the same thing you are saying about frequency, because frequency is directly proportional to the pitch. I'm hoping that we are moving together, and now you can see how this Doppler effect occurs. Now, if you are to look at these wavefronts, they will nicely show you a Doppler effect. Let's say this is our ambulance, it's moving towards the listener. So we're having the listener here who's stationary. You are having the source, which in this case our ambulance is moving towards. What happens? You can see that the wavelength decreases. So you see the wavelength, you can see that the space there, very small. You can see the wavelength has decreased. The wavelength has decreased, which means we're moving towards. Remember, I said the wave equation is very much important, which is V equals to F lambda. So at all times, you will have that equation in your mind to say, okay, as the wavelength decreases, what happens to the frequency? It increases. Hence, we are saying always remember that wavelength is inversely proportional to the frequency. So they are inversely proportional to one another, if I can put it like that. As the wavelength increases, the frequency decreases, as is in this case. So it means this listener, as the ambulance is moving towards the listener, what will happen? The wavelength decreases. As the wavelength decreases, the frequency increases. And if frequency increases, it means the listener will hear a high pitch of sound. So the sound will be highly pitched. So it's very much important to understand that it is the decrease in wavelength that makes the frequency to increase. So the same as the car passes our listener here, you can see that our ambulance is passing now. The wavelength is starting to increase here. You can see even on these waves here, or if you want to look at that one, you're able to see that our wavelength now is increasing now. You can see now the wavelength is increasing. As the wavelength increases, what happens to the frequency? It decreases. Hence now, when the wavelength increases, the frequency increases. When the wavelength increases, the frequency will decrease. In this case, the wavelength is increasing, the frequency decreases, meaning that we're going now to have a low pitch. The pitch will be low because now the ambulance is moving away from the listener. So it's very much important that you keep that in mind at all times, and then you will be able to understand this topic. As we were saying, just to talk about wavefronts going forward, to say the direction of movement of the object. So you can see as the object is moving there, you can see that the wavefronts are compressed ahead of the source, hence will have a pitch will be higher because the frequency is high. So you can see when the wavelength, so the main thing that you are looking at is the wavelength. When the wavelength is small, you know you have a shorter wavelength, means higher frequency. Then you see that shorter wavelength here, higher frequency. But as the source passes, the wavelength starts to increase. And when you have a higher wavelength, you will have a higher wavelength. You will now have lower frequency. So you're able to see that the frequency will be low, and if frequency is low, the pitch will be low. So the main thing is pitch and frequency, they move together. Wavelength is opposite of them, is inversely proportional. To say if the wavelength is higher, the pitch will be low because the frequency is low. I hope this slide helps you to understand that. Now, again, I want to emphasize with this slide to say if you have a stationary source and listener, so you have your ambulance that is just somewhere there, not moving. They are all stationary. Even the listener is stationary. There will be no change in frequency. And if there is no change in frequency, there is no Doppler effect by definition. Remember, we said for Doppler effect to happen, there must be change in frequency, because Doppler effect is change in frequency detected by the listener because of the velocity, the different velocity of the listener and of the source. So it's very much important to say, because all of them are stationary source, stationary listener, no Doppler effect. Or a listener is inside a moving source, so they will be moving with the same speed, because if you are inside the same source, then it is the same speed that you are moving. Then we'll say there is no Doppler effect there. So hence we are saying the frequency is equal to the wavelength. Is equal to, so the frequency is the same, the wavelength is the same, and then there will be no relative motion between the source and the listener or the observer, and then true pitch of sound. So it will just be true pitch of sound. Remember what we're saying. We're saying the source of sound will produce a certain frequency, but a listener who is listening, if there is no movement, there will be no change in the frequency. And if there is no change in frequency, there is no Doppler effect. So you got to understand, hence we are indicating that situation in that way. I hope you get it. Now, if we have a wave front that with a source that is moving towards a stationary listener, you will see that towards, we said, the wavelength decreases. So towards, the wavelength is decreasing, which meaning that the waves now are compressed. So you don't have the waves that are longer, they are compressed in a short space, and hence the frequency increases. So you have that at all times. Don't forget, the velocity will remain constant. Hence, we are saying the pitch of sound increases. So whatever happens to the frequency happens to the pitch. If the frequency increases, the pitch increases. And the pitch increases when the wavelength decreases. So I've overemphasized that. Indicated there, we have our listener, and then you can see our wavelength is decreasing. When the wavelength decreases, we're saying the frequency will increase, and when the frequency increases, the pitch of sound will increase. So that is the relationship. But now, when we have a wavefront of a source moving away now, so when a source is moving away from a stationary listener, we're saying the wavelength increases, which means the waves are stretched. So you no longer have a wave that is like that. It's now opening up. Your wave now is opening up. So you can see that it's no longer stretched. Hence, we're saying that the wavelength is increasing. And when the wavelength increases, the frequency decreases, our velocity, our speed, we said it remains the same. And then we are saying the pitch of sound will decrease. So when the frequency decreases, the pitch of sound decreases, the wavelength increase. So don't forget that relationship between those three variables that we're talking about. As we're indicating, you have our listener here. You can see that our source is moving away. And when it moves away, what is increasing is the wavelength here. The wavelength there is increasing. As the wavelength increases, the frequency decreases and the pitch of sound decreases as well. So I hope you have got that, and you will be able to move with that information. When we start solving problems, you will be able to remember. And always I will look at the wavelength to say, what is happening to the wave? Is there change in wavelength? When there is no change in wavelength, we're saying no Doppler effect, because the wavelength must either increase or decrease. And we're saying it decreases towards and it increases away. So if it's away, the wavelength increases. If it's towards, the wavelength, you can see if it was moving that side, the wavelength will start to decrease. And if the wavelength decrease, the frequency increase. So I hope now you are, in your mind, you have many increases and decreases, because we have talked about that a lot. And I hope it will help you. Now, where do we use this Doppler effect? It's used by the traffic department, where they are using the speed traps. So you see the speed traps. So you can see that our science is in practice. We're not just doing science that end in the classroom. At least you are able to apply this science. So these are some of the application of these science. We're saying the blood flow rate can be measured as well using Doppler effect. So you can see Doppler effect is important. The speed of the planets and the stars can be determined using Doppler effect as well. And then we are saying it can be used. We talked about this first application where we said you can use Doppler effect to check the heartbeat of the unborn fetus in the womb. So this is very much important for the goodness and health of for the children, unborn babies. We're able to see the heartbeat, whether there is something wrong with them or not. We're able to use Doppler effect. So hence I think you are happy and excited that you are doing this topic. That really, really helps even in our speed traps, even in our health medical field. And it's used in the weather stations to detect precipitation. So you can see there are many uses of this Doppler effect. And we are saying you must be able to remember all of them. It's used for speed traps, for blood flow rate, and is used for the speed of the planet, of the stars. It's used to measure the heartbeat of the unborn fetus in the womb. It's used in the weather station to detect precipitation. So don't forget these uses of Doppler effect to say it is very useful. And now I think you understand why we are doing this Doppler effect. Now, let's look at the redshift, what we refer to as the redshift. As we started when I was going through the exam guideline, I've shown you that we'll be dealing with the redshift. So we won't be focusing on the blue shift, we'll be focusing on the redshift because we have the redshift and the blue shift. But for our syllabus for grade 12, our focus is the redshift. Now we're saying this is the shift in the spectra of distant galaxies towards longer wavelength, towards the red end of the spectrum. So if you can look this spectra that is given here, you can see that as we move away, look, this is our wavelength. We have a wavelength of 400 nanometers, wavelength of 500 nanometers, 600 nanometers, 700 nanometers. So you can see that as the wavelength increases, we're moving towards the red. You can see here this side is red. That's the red shift. Is when the wavelength increases, we're moving towards the red shift of our spectra. And then as you move this side, you are moving towards the blue. And I've indicated that our focus is the red shift. But if the wavelength is decreasing, it means we talk about the blue shift. But for our case, we're saying the wavelength is increasing. We are going to look at cases where the wavelength is increasing or the cases where the stars are moving away from the Earth. And so I'm referring to it as the expansion, as the universe is expanding. So we're saying the Doppler effect is a characteristics of all waves, including light. And we're saying all light emit white light and stars moving away from the Earth. So if the stars are moving away, it means the wavelength is increasing. And as the wavelength increases, we are saying that we are moving towards this. We can refer to it as redshift. This will display the light with longer wavelength. So longer wavelength, which is the red colors of the spectrum, due to the Doppler effect. So Doppler effect, we are saying here, when we have longer wavelength, it means it's redshift. When we have a lower wavelength, we are talking to the blue shift. And then it's important that you remember that. And we're saying astronomers have found that all stars exhibit a redshift. So all stars, they have a redshift. It means they are moving away. It means the stars are moving away from the Earth. It means that the wavelength is increasing as the stars moves away, because we said away, the wavelength increases, towards the wavelength decreases. And as the wavelength increases, we said the frequency is decreasing. So you are able to remember that. And then we're saying they are moving away from the Earth and from each other. This suggests that the universe is expanding, because if the stars are moving away from the Earth, so it means where we are now, there's expansion of the universe. So I hope you will be able to remember this spectra. When you see it, the blue shift, the red shift. The main thing that you have to remember is the wavelength. To say as the wavelength increases, is red shift, we are moving towards the red, and then as it decreases, we refer to the blue shift of the spectra. So I hope you will remember that when you get this question, and then you will be able to answer questions. Now, with no wasting of time, we're going to spend more time on activities, because in your exams you will be doing a lot of activities. So I'm hoping that you will do activities and you will practice as many questions. If you can just give us that 15 marks of Doppler effect, we will be happy with that. Hence, we are saying it's important that you spend time dealing with Doppler effect. So let's look at this question. It says, in which direction will an absorption spectra shift during a redshift? We just talked about redshift now. Now you get this a multiple choice from previous exam questions. So it's important that you know how to answer multiple choice questions. Now, remember, multiple choice, you are given 4 options. Of the 4, we are saying 2 are just there to distract you. We refer to them as distractors. So we'll always advise you to eliminate the distractors because they are not answers. They won't be answers. They're just there to distract you. Remember, you have 25% chances. 1 over 4 is 25% chances of getting a correct answer. But if you remove 2 distractors, you will now have 50% chances of getting the correct answer. So we are saying it's very much important that you do that and you are able to increase your chances of getting the correct answer. Now, we're talking about redshift. This question is about redshift. We just talked about it. And if you remember, we said redshift has to do with longer wavelength. So the first thing that we're looking at is a longer wavelength. And we said when the wavelength is longer, we said that the frequency decreases. Remember the relationship using the wave equation. We said that the frequency is inversely proportional to wavelength. So longer wavelength, which is redshift, we are saying that the frequency must decrease. Let's look at the options that were given. They said that in which direction will the absorption spectrum shift? This one is saying it will shift towards the blue end of the spectrum. So you can see that this one we said redshift. During a redshift, you can't be moving toward. I remember redshift we said is longer wavelength. So blue end it will mean a shorter wavelength. So that is number A. It's a nice distractor. We just remove it because there's no way it can be the answer. Now let's look at option number B. It says it will move to the light of a shorter wavelength. You see, B is telling us the same information as A because shorter wavelength means blue towards the blue end of the spectrum. So all these two, A and B, you can see that they are not answers because all of them they are referring to the blue end of the spectrum where we have shorter wavelength and we have the blue shift. That now let's look at number C. C says it will move towards light of a lower frequency. So I will stop on that one. Let's look at D again. It says it will move towards the light of higher energy. Now let's check all that because it's very much important for you to remember that if the light of lower frequency means longer wavelength. So you're able to get it from here to say, okay, because here we're having a longer wavelength, it means we have a lower frequency. Hence, number C becomes our answer. And you are 100% sure that you got that answer. The main thing that we are looking for is longer wavelength. But sometimes in the question like this one, we didn't talk about longer wavelength. We talked about a lower frequency. You must know that lower frequency means longer wavelength, which talks to the redshift. So I hope you understand number C, and then as you practice as many questions as you can, you will be able to remember this type of equation, and you will be able to do it. Now let's go to our second activity. Now this is a structured question. It says a police car moves away from an accident scene at a constant speed with its siren on. A paramedic at the accident observed 7% drop. You see some maths there. 7% drop in the frequency of the sound of the siren in comparison to when the car was standing still. So the speed of sound in the air on that day is 335. Remember when I started, I said speed of sound is V is 340. So don't expect that. You see, on that day, remember we said it depends on air and all that. You will check that the density of air is not always the same. Hence, our speed cannot always be the same. Hence, we're saying on that particular day, the speed of sound was 335 meters per second on air. So always check the speed that is given in the question, except when you are asked to calculate that particular speed. So we are given the speed. The second thing that we are given the 7% drop. 7% drop in the frequency of the sound. So you have to remember that we have 7% drop, which means we no longer have 100%. Remember, when you are having 100% of sound, you are getting everything. But when it drops by 7%, so the likelihood is that you will feel that you have 7% of that sound. But that won't be correct. We are saying it means you have 93% of that sound, because 7% dropped, which means it's 100 minus 7. Then you are remaining with 93 over 100, which will give you 0.93. So I think it's very much important for you to understand that 7% drop means we no longer have 100% of the sound. Our sound is now 93%, which is 93 over 100. Now, you have seen what I've done. I've started by explaining so that you are able to remember the question as well, so that we don't have problem. Now, it says state in ways the Doppler effect. So it's very much important that that definition, you know it, you sing it, because we don't have many definitions in terms of this question of Doppler effect. So it's very much important that when you go to question 60, which is this question, you are able to define what is Doppler effect. Remember, we said it's the change in frequency. We said it's the change in frequency, or pitch. So you'll say change in frequency or pitch of sound, that frequency of sound detected by the listener. Because of what? Because of the different velocities of the listener and the source in that medium relative to the medium of propagation. So it's very much important that you know and you sing that definition, which is this one, which is saying it's a change in frequency or pitch of the sound. If you look at the formula itself, it will talk to all this that we are talking to say this is change in frequency of the sound detected by a listener. Hence, we have the listener on the left of our equation, because it's the change in frequency of sound detected by a listener. So it is the listener who's detecting that change in frequency, because the sound source, if you look at the formula itself, we said V, which one, this one we said is the one of medium of sound, is of the medium here of sound of propagation, which we said in the air, in this case it was 335. But now we said now let's detect, because the listener and the source have different velocities. Hence we're saying we have the velocities plus or minus VL over plus or minus VS. So the two must have different velocities for us to have a change in the frequency. So change in frequency detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So sound propagation is only this V that we're talking about, these two V's that we're saying they remain constant. In air is 340. So for that one, which is our medium of sound propagation, we're referring to that. But in your definition, you're saying what is Doppler effect? You're saying the change in frequency detected by the listener. This listener, depending on what? Because we are saying because the listener and the source have different velocities. The listener and the source have different velocities relative to the medium. The medium of propagation is this V, which remains constant. So I'm saying, as you look into that definition, please remember that you can be able to remember how to define Doppler effect by looking at that. So we're saying it's the change in frequency of sound detected by the listener. As the listener, this is the one that is detecting that. Why? Because the sound and the listener have different velocities relative to the medium which this V depends upon, relative to that medium of propagation. So I hope that helps you. Now you have your question which says calculate the speed of the car. Now you will know that we have our Doppler effect equation, and then you do your data collection. Don't forget we're given 7% drop, which means now the listener the listener has a frequency that is not 100%, but that is 93% of that. And if you say 93 divided by 100, you'll get 0.93. So our Fs is 0.93 compared to the Fs, which is the frequency of the source. And the first thing that we do, we said we copy the formula as it appears in the data sheet. So just go and copy it with a plus or minus. Don't commit too fast, because we want to give you this 1 mark of writing the of writing the formula. So it's important that you first write the formula as it appears in the data sheet. I think that is a simple instruction that you will be able to follow. Sorry for that. So remember what we said. Our frequency of the listener, we said, is 0.93. It's 93% frequency of the source. So it means the frequency of the source is Fs, which is 1 Fs, but the frequency of the listener is 0.93 Fs. So that was a trick question. It was just tricking you because of the 7% drop. So that drop, we're saying out of the 100%, it dropped by 7, which means we are remaining with 93. 93 over 100 will give you 0.93 Fs. Hence, now you can see, because if you look at this question, you are going to think that we don't have enough information to solve the problem, because we were only given the drop and the V. But look at what we have. Now we're having 0.93 Fs. The speed of sound that day, they said it was 335. We said it's this one, depending on the medium of propagation. And then because now a police car moves away, so it's moving away. Remember what we said? We said away means minus over plus. It means minus on the numerator, plus on the denominator. So when it's away, we want to have a bigger number that we are dividing with. Hence, it must be plus there, because we want the frequency of the listener to be small. So it's very much important to know that it's 335 minus 0. Why 0? Because the source was stationary. And then you have, again, you substitute the V there, which is 335 again, plus Vs, which is what we're looking for, multiplied by Fs. We're just left with a simple math question there, which I think you can look at it and be able to do that question. The first thing that you can do, you can divide both sides by Fs, so that your Fs just disappear because it appears both sides. Then you can just cross multiply, where you will say 0.93. You multiply it by 3.35. Remember, it must multiply everything that is in that bracket. So it's 0.93 times 335 times Vs. That will be equals to, remember, under this 0.93, we have a 1. So you cross multiply with that 1 to say 335 minus 0 times 1, then you get that. Then you are able to do the maths and you are able to get our answer, which, when we have done it correctly, you will get our speed is 25.22 meters per second, which is our Vs. So I hope you have seen how to use this formula to solve the problem. The main thing that I want to overemphasize is the plus and the minus. To say if it's away, it will be minus at the top in the numerator, and it will be plus on the denominator side. So if you get that one correct, to say when it's towards, this is what we're going to do. 335, you are able to substitute 335 because it was given. And then the listener, remember when I started, I indicated that we have the listener. If the listener is moving, our source is stationary. So you're able to see that which one is moving. It's a police car that is moving, which is the source now, the source of that sound. The source was moving, meaning that the listener was 0. Hence, we wrote 0 there. The source, we're looking for the speed of that particular source. So I hope this first question is able to open your eyes and make you want to do as many problems as you can that has to do with Doppler effect. Now, an astronomer on Earth observes the missing frequencies in a line from a distant galaxy. The frequencies associated with the specific elements are lower than expected. So the frequencies are lower than expected. They are lower than expected. Already, you are starting to think, to say, okay, when frequency is lower, what does it mean? What does it apply when it comes to the wavelength? Because if frequency is lower, it means we have a higher wavelength. And we said higher wavelength or longer wavelength, is better to use the word longer because we're talking about distance here. A longer wavelength will mean that we are shifting towards the red end, which is the red shift. But we said shorter wavelength will mean blue end. So it's important here when you see that the frequency associated with specific elements are lower. So when the frequencies are lower, already you know that frequencies lower means longer wavelength, which will now refer to that red shift that we talked about when we started with our lesson. Sorry if I've given it away, but I want you to look at the question and you are able to look at that. With what kind of light spectrum is the astronomer working on? We said we are working with the absorption spectra, which in this case is the answer was answer only absorption or emission. So you know that we're working with the absorption spectrum. The next question was identify the type of shift seen by the astronomer. So you have to identify, is it a red shift or a blue shift? Remember, we said you're looking at the wavelength. And if you know the wavelength, you know the frequency. But in this case, we're given the frequency. They said is lower than expected. When frequency is lower, it means longer wavelength. Then you will have known that that must be a red shift. So you can see that you are able to collect your marks. And then the next question says, is the distant galaxy moving towards or away from our solar system? So remember, again, the concept of the wavelength, to say as the wavelength increases, it means, remember we said the universe is expanding. It can only expand if the stars are moving away from our solar system. So that must be away. So you can see this was the question paper, and then end of the year question paper that learners wrote, and then you can see how much marks you are going to collect if you do that. Hence, we're saying spend more time dealing with this Doppler effect, and then you will be able to understand. So I'll just take a short break. Then when I come back, we'll do even more activities based on this Doppler effect formula. Thank you very much. back. I hope you now understand the redshift. That we emphasize that redshift simply means frequency is lower. When the frequency is lower, we're saying we have a longer wavelength. Longer wavelength, shorter, lower frequency. So don't forget that longer wavelength, lower frequency means we are shifting towards the red end, or the red shift is a red shift. And then we said this is part of our absorption spectra. And then we said identify the type of shift. You said it's red shift. And we said, is it moving away or towards? We said it's away. It's away because the wavelength is longer, which means it's moving away. So don't forget, I think we've overemphasized the issue of this question. Now we're saying activity 3, a group of learners experimented to determine the speed of sound. So this is the purpose. They wanted to determine the speed of sound on a particular day. You can see we said even if it's on air, but it will depend as well on that particular day to say is it 340, is it 335 like we've seen in the previous question. So you're able to see that our speed can be around 340 as long as it's on air. At a particular point, we're saying they place a sound source emitting at a certain frequency. One learner walks. Remember, it's one learner now who is walking away. One learner walks away, but it was a group of learners. Not all of them were walking away. It's one. One of them is walking away from the sound source. So we have one learner walking away from the sound source at a constant velocity. We said our speed is constant with a detector that registers the frequency of the sound detected. The graph below shows the detected frequencies versus time. I think it's very much important for you to understand to say, okay, as we started here, we had the frequency. We have the frequency before that. Remember, when all this group of learners were at a particular point, all of them, there was no Doppler effect, because Doppler effect will only have Doppler effect when there is a movement, when there is a change in frequency, when there is a change in the wavelength, whether it's increasing or decreasing. So in this case, you can see that we started with a frequency of 871, and then we have a frequency of 850, which you can say is the frequency of the listener. So if the source produces 871 hertz and the listener is hearing 850, already you can see that the frequency is decreasing. And then as the frequency decreases, then you know that the wavelength must be increasing. Remember, they are inversely proportional. So when the wavelength increases, or when you have a longer wavelength, it will mean that it's walking away. As the statement said, one learner walks away. So it's walking away will mean we're having longer wavelength, which means that we are having to have lower frequency. You can see the frequency now becomes 850. That is registered by the listener. So even if you can look at the definition itself of Doppler effect, to say Doppler effect is the change in frequency, you can see that we're starting with 871, is changing to 850. So hence we're saying Doppler effect is the change in frequency of sound detected by the listener. So the listener detects the frequency of the listener, this one is 850. So the listener, which is that learner who walks away, is detecting 850. So there is a change in frequency of sound detected by the listener. Why is it like that? Because the listener and the source have different velocity. And then we said relative to medium of sound propagation. So the sound propagation in this case, we're on air, so we're expecting that it will be around 340, depending on that particular day, how much it is. So now if we look at the question, they said no. This graph below shows the detected frequency versus time. So frequency versus time. So the first question there was, write down the frequency of the source. So you will have known that the listener, which is that one learner who's moving away, the listener is moving away. Obviously, if you are moving away, there will be decrease in terms of the frequency of the listener. Hence, you will look at it that way to say, okay, if the learner is moving away or is walking away, the frequency there must decrease. So the one with a smaller frequency must be the frequency of the listener. 871 is the frequency of the source. So you're able to respond to that question 3.1 by saying that the frequency of the source will be 871. Now let's look at 3.2, which says explain in terms of the wave motion, why the detector registers different frequencies. So why do we have different frequencies here? So this question needs you to explain the whole principle of Doppler effect to indicate that as this learner now is moving away from the source, the wavelength will now start to increase. When the wavelength increases, will mean that they will have a lower frequency. Hence, we are having the frequency that is lower than the first one that we had. Hence, when you look at how the question is answered, we are saying we have 871 hertz for the source, but we are saying as the learner stands next to the sound source, when the learner is still here, the detector registers the frequency of the source because there is no relative motion. So when there is no motion, when the learner is still with the group here, he will register 871 because there is no change. There is no relative motion between them. As the learner moves away now, the learner starts to move away, you can see that now the source, the waves become stretched out, which means we have a longer wavelength. The wavelength becomes longer and the frequency becomes lower, which is what we talked about. So we can see that it is still the same. This question 3.2 is as good as like you are defining, you are just describing what happens during a Doppler effect. Now, if you look at the question as it continues, we now have for 7 marks, another learner records the time taken for the first learners to move from the point of sound source to a particular point. The graph below shows the position versus time graph of the motion. So you can see we have our position there, we have our time that side. And then the question is saying calculate the velocity of the sound on that day. You can see that it's a 7-mark question, which tells you that this must be a multi-step question. If you look at the given information, you will see that the information that we are having will be very little. If you look at the previous question that we had on the statement, we just given a group of learners experimented to determine the speed of sound on a particular day at a particular point. They place a sound source emitting at a certain frequency. One learner walks away from the sound source at a constant velocity with a detector that registers the frequency of the sound detected. The graph below shows the detected frequency versus the time. So you can see we have two things now from this graph. We have 871, which is the frequency of the source. We have 850, which is the frequency of the listener. So as you go to 3.3, you go with that information to say, I'm going to 3.3, but there is something. You're not coming empty here. You're coming with the frequency of the source, which you said is 871, and the frequency of the listener, which is in this case 850. Remember, frequency is measured in hertz, so you must be able to indicate is 871 hertz and 850 hertz. So you are coming with that information, and the question that we are having is saying here, let's calculate the velocity of the sound. So you have, if you look at the formula itself for Doppler effect, which we said is frequency of the listener, V plus or minus VL over V plus or minus VS times Fs. So that is our formula. So you will see that in this formula, we already have FL, we already have Fs. Those two we have. But now we want the speed of sound that day, the velocity of sound that day. So we want this one for that particular day. So, which means we must first be able to calculate the velocity, one of these two, using this graph. So this graph is there to indicate that because you have this variable you have, that's number one. Number two, you have the other 3 variables. You can only have the one. Remember, what was moving away was the learner. The source was stationary. So you will see that the source here is not a problem because it was not moving, but the learner was moving. So for us to answer this question, because we are looking for this V, we must first be able to calculate the speed or the velocity of the learner, and that information on the graph can be able to help us in terms of solving the problem. Now, if you remember your science, how in grade 10 you were calculating your velocity. In fact, by definition, you are saying velocity is the rate of change in position. So you are able to see that if you are having delta x over delta t, that will be able to give you your speed, and that will be your speed of your light. So you are able now to use this information that is given here, because we are having a position there 110, we're having a position there 94, and the time is given as well. So you can see that you can be able now to determine the speed before you go to use this formula, because for you to use this formula you will need to have another variable. So remember, you have two variables there, which is the speed of velocity of sound, this v that we are looking for. This v is the one that we are looking for, but now you have vl that you don't know. You don't know vl. Vs, you know that the source was stationary. What was moving was the listener. So you can now be able to calculate the speed of the listener first, or the velocity of the listener, which is delta x over delta time. If you get that, you can be able to come and substitute in the formula. Then you will be able to solve the problem. I'm hoping you are, as I'm speaking, you are trying to look at how can you go about doing that. It's a nice question. You're able to say, okay, our change in x is 100 minus 94. 110 minus 94. 110 minus 94, I think that will give you 16. Yeah, it will give you 16 over change in time. We have 8 minus 6. 8 minus 6, that will give you 2. 8 minus 6 is 2. So you're able to do that. Then you can be able to do your equation to say you have 16 divided by 2. Then what is your speed of your sound? Then if my math is well, 16 over 2, that will give you 8 meters per second. And then you can be able to go and now substitute there. Then you no longer have many unknowns. You can be able to calculate the speed. Now, as we go to the solution. Remember, this question was 7 marks, so you can see that it had a lot of marks that you were supposed to do. As indicated, you are able now to calculate. You are able to first be able to calculate the VL, which is changing x over changing time. You had your 110 minus 94 from the graph, changing x there. You're able to get that. 8 minus 6, so you're able to get that one. Then you get your 8 meters per second. You can see why now it was 7 marks, because you were allocated 3 marks that you were supposed to receive from this question. So you're able to see that you have 8 meters per second that you got. Now you can be able to utilize the formula. Remember, what is very much important is the issue of plus and minus when you are given the data sheet. When we said the first step, you copy the formula, which is your FL, which is V plus or minus over VL, V plus or minus VS times Fs, which is the frequency of the source. So it's very much important to make that decision to say, is this towards or away? Remember, we talked about that. We say, okay, if it's away, the learner was moving away from the source. So that will be minus over plus, which means from our formula, our FL will be V minus VL over V plus Vs times Fs. So don't forget, away is minus over plus. Towards is plus over minus. So immediately when you have done that, you are able to come and say, okay, now the listener was moving, but the source was stationary. Hence, it must only be V here. Hence, our formula will become Fl equals to V minus VL over V times Fs. You see. So we would like you to instead of just giving us this as a formula, first write the formula that is given in the data sheet. I think I've overemphasized that so that you are not able to, you don't lose marks, because you can make mistakes when you're changing the plus and the minus, and then you are not able to get that mark. Now you are able to write the formula, you get a mark for that, and then you know that the frequency detected from the graph, it was 850, the one that is detected. And then we know that the V is what we're looking for, minus 8, we got 8 meters per second using that graph. So it's V minus 8 over V times 871. I think you will practice many of these questions so that the maths part, because the only thing that is going to be a problem for you is to do the maths. The substitution, I'm positive that when it comes to substitution, you'll be able to get the 850 there substitute on the right correctly, you will get 3 marks. But the only problem that you might have will be to make that V subject of the formula, which is the skill that I think is important that you look at it. Because if you are having something like that, the first thing you must know that you have 850, which means it's 850 over 1. Remember, under any number there, we have a denominator of 1, which is equals to, then you are given in this side V minus 8 over V times 871. I want to show so that you know how to go about doing this. So what you have to know, under this 871, you know we still have a 1 there, which is V times 1 is V. So you can see that what we are really having here, we're having V minus 8 times 871 is equals to 850 V. 850 V. So that's what we are having. Then you have to remove the brackets. When you remove the brackets, you'll multiply everything. 871 times V, 871 times 8, you're able to multiply all of them there. Then you are able now to take everything that is a V to one other side, which will be your 850 minus 871 V. Then if you take it the other side, then you are able to now make V subject of the formula. And if your maths is correct, you are able to get V equals to 331.81 meters per second. Remember, now you must always show us the unit. Remember, we're emphasizing that your mark, you will always have a mark for formula, you will have a mark for substitution, the mark for your answer with correct unit. Remember, for you to get that final mark, the SI unit must be correct. Then you are able to receive all those marks. Now, I think our 3.4 question was on the use, name two application of the Doppler effect in the medical field. I think we've talked about this when we started with the lesson. We talked about the footers to say when we're checking the heartbeat and all that, we are able to utilize Doppler effect, which is what we have on this answer here, to say it's used to measure the direction and the speed of the blood flow in arteries and vein, is used to monitor the heartbeat of a newly formed fetus. So we said when the babies are unborn, we can check their heartbeat using the Doppler effect. As well, we are saying that it can be used as well to measure the direction and the speed of blood flow. Remember, this question was specifically in the medical field. Sometimes you'll get open-ended questions where we don't say in which field. You can talk about your speed traps and all the other things that we talked about. So it's important that you always remember the applications. Remember, when I started this topic, I indicated that we have only 6 bullets that you have to know. So just practice and make sure that that 15 marks, you come with it, all of it, and then that will be your 10%. Remember, if you have done well in Doppler effect, it will mean you have 10% of the whole question. Now, we can move to the next question, which in this case is activity 4. We are having a car. A car moves at a constant speed of 10 meters per second. Always have a highlighter towards you so that you are able to highlight whatever the values or the what we are given, the given information. The car is moving towards a stationary source. So I think that one we discussed, we agreed that if the source is moving, the listener must be stationary. If the source is stationary, the listener must be moving. So always check which one is moving between the two. So in this case, we're saying a car moves at a constant speed of 10 meters per second towards a stationary sound source. That towards, you see, it's in capital letters. But as we move forward, we're moving in a direction where we won't be giving you the towards in capital letters because we're making it obvious to yourself that it's moving towards them. But we're showing the importance of the towards. But as we move forward, you will see questions that we'll be seeing in the coming future. They won't be towards in caps lock. It will just be towards as part of the statement. So we're saying don't rely on the capital letters. Just know that as you read the statement, you are looking for towards, you are looking for away. Sometimes we use the word approaching, deproaching, and all that, so that you are able to know that towards is approaching, so that we don't have problems in terms of that. So in this case, the car was moving towards a stationary sound source. So you can see that in this case, the car is not the source. The source sound source is stationary. So don't make a mistake that always the car, where the car is, because of the ambulance that we have done and all the others, you think that always when you have a car, it becomes the source. No, the car is not the source. In this case, the car, we're having a listener in the car. In the car, we have a listener, and then sound source is at B and is stationary. Remember, what is moving is the car. Then, which means the listener is moving in this case, which means V is 0, Vs is 0 meters per second, and then 10 meters per second is for Vn. So that is your data collection that you must do as you start the question. And then we are saying the sound source emits sound waves of frequency 880 Hertz. So the source, this source that is stationary here, we're saying it has a frequency of 880 hertz. That is the frequency that is produced by that source. As the car is moving with 10 meters per second towards the sound source. So now we're saying a sound source A is attached to the car. A sound source detector, a sound source detector A is attached to the car. So we have a detector that is attached to the car here. It's written A, that's our detector there on top of that car. And another detector B is attached to the sound source. So you can see this is very interesting. You have another detector. So you have detector A and detector B. A is on the car that is moving. So A is in the movement. B is with the stationary sound source. Now we're saying detector B detects the sound waves reflected from the car. Okay, detector B detects sound waves reflected from the car. The speed of sound in air is 340 meters per second. We talked about this one. It will be 340 or around 340, depending on that particular day. So now we are saying state the Doppler effect in ways. So you can see that this 2 mark is almost always there. If we don't ask you to state it, it will still be a question that will want you to apply it. But at the end of the day, with that definition, you know that you will secure your 2 marks. So you will define your Doppler effect, which we said is the change in frequency of the sound detected by the listener because of different velocities of the listener and the source. So the listener and the source have different velocities, and then we are saying relative to the medium of sound propagation. So it depends on that medium that we are moving. In this case, we are in air. The medium is air, hence it will be 340, which is our velocity of the source. I mean, velocity of the medium, which is V. It will be 340, which is constant, which is the velocity of sound. Now you are able to state Doppler effect for 2 marks. You can see almost all the questions, I think, except one that we have done, have wanted you to define Doppler effect. So you know that when you know Doppler effect, you can be able to get your 2 marks. And then we have a question, at least for the first time, we have a question that says, calculate the wavelength of the sound waves emitted by the source. So the sound source had a frequency of 880. We know the speed of sound is 340. You will have seen throughout the question that sometimes we refer to V as the speed, sometimes we refer to V as the velocity. Remember the difference there is just the issue of the other one is a scalar, the other one is a vector, but we're still referring to the same thing, which is the V, which is our, either you will refer to it as a speed or as a velocity. So don't be confused to say in other questions they talk about this velocity, in other question we're talking about speed, but still referring to the same thing, which is your meters per second there, which is 340. So you have the speed of sound. Remember we said V equals to F lambda. So for the first time we have a question here that says calculate the wavelength. So you got to always know that when you say calculate wavelength, we have a formula that is wavelength. And for you to do that, you need V, which were given as 340. You need the frequency, which are given as 880. So you see, you are able to answer that question because you can be able to calculate now the wavelength because the other two variables are given. So it's important that you always look for given information first, then before you choose the formula that you will utilize. So I think this formula can help you to answer that question, you just do the substitution and then you are able to calculate the wavelength. Now, the other question that we're having is saying calculate the frequency of the sound waves detected by detector A. So now we're going to do the actual calculation of the frequency of sound. Frequency of the sound waves detected by detector A. So that is FL. So you know that for FL, you're going to use the Doppler equation, and then we're able to substitute in the Doppler equation. Now, I can say in this manner, we talked about this one to say the V there is V equals to F lambda, which is your wave equation, and then you get 1 mark for writing the equation. For substituting, the 340 was given, the 880 was given. So it becomes much easier for you to be able to collect those marks because everything was given. Then you are able to calculate the wavelength, which is 0.39. Remember, we always advise you to round to two decimal places. So remember those two numbers after the comma. We are saying that is the 2 decimal places that you must round to. And then the question that says calculate the frequency of the sound waves detected by detector A. The first thing, which is more important, is for you now to look at the question of towards or away, whether it's going towards or away or what is happening. Then you are able to do that with no problem. So you're able to do the substitution in this case, and then you substitute. You are given FL equals to V plus or minus of VL over that, and then you had a car that was moving towards. Remember towards, this was from our previous question. Towards, we talked about towards to say as the car was moving towards, then we're talking about the detector A, that A will detect. So its towards is FL equals to V, but because it's towards, we said it must be plus over minus. I want to put more emphasis on that to say towards, it must be plus over minus. Plus over minus, we know that the speed is 340. 340, we're given that one. We're looking for FL in terms of this question. We're calculating the frequency of sound waves detected by A. So you're able now to say, okay, it's plus, and then which one was moving? The source was stationary, so it means it's V minus 0 there, but the listener was moving with 10. So you're able to see that is multiplied by 10. What was the frequency of the source? It was 880 hertz. So you're able to do a simple substitution, and then you are able to get your answer, which now you just have to do the cross multiplying and all that, because when you substitute, you're going to have your FL equals to 340 plus 10, which is 350. Then you have divided by 340 times 880. So it's just a simple calculation that you can do in your calculator. So you are able to look at it and say, this is how you go about doing it, and it's just straightforward. So you can do as many problems as you can. And then we're saying the last question was the sketch graph below shows the frequency recorded by detector A. So detector A had that frequency, and then the question was redraw the graph above for detector A in your answer book on the same set of axes and sketch the graph of the frequency recorded by detector B. So you will be able to see that detector B, which was having higher, then you just have to draw the graph for B at the top there. Then you are able to get that 2 marks. So at the end of the day, you are able to answer the whole question. Now, I want us to look at the whole process of what we've been doing throughout this lesson. The main thing that we talked about, we said, let's look at your prior knowledge to say, as you leave your grade 10, you had things that you have done in grade 10. You have done the longitudinal waves, and we said that you have done as well the wave equation, which gave us that V equals to F lambda. So you are coming in grade 12 with that information that V equals F lambda, and because of that, we said V is the speed of sound, and the speed of sound, we are saying it depends on the medium where the medium of propagation. So I indicated to yourself when it's in a still, when it's in air, and when it's in water. I think in water we said it's 1,500 meters per second. When the sound is moving in a still, we said about 5,900, and then in air it's around 340. But you have seen that 340 meters per second that we had, that we talked about in terms of the speed, we said it depends on, because these days the humidity and all that is not the same every day. So sometimes it will be 335, 331, but around that 340, so that you are not shocked when you get an equation. They are saying in that particular day you have a speed of sound in air that is less or more than 340. So you have to know, but it will always be around that 340. That is the first thing that we have emphasized. The other thing that is very much important about our lesson was the definition of Doppler effect itself, which we have emphasized that, don't forget, from the Doppler equation itself, which is FL equals to, which is this one that I've written here, so that I can explain from there, you are able to see that this is the change. So we're saying Doppler effect is the change, S is needed there, is the change in frequency of sound, change in frequency of sound detected by the listener. So we're saying this is detected by the listener. So you see, this is the listener that is detecting the sound. That, why is it so? Because there we are saying, because the source and the listener have different velocities or different speed. They have different velocities. The source and the listener have different velocities relative to the medium of sound propagation. So don't forget that definition. You must just sing it and always know it. The Doppler effect equation, always we are saying go to the data sheet, copy it as it appears in your data sheet, and be able to write it and start to change. Remember, we said as the between the source and the listener, one must move, the other one must be stationary. If the source is moving, we said your VL will be 0. If your listener is moving, your VS will be 0. And then you are able now to go and do your calculations. The main thing that we're emphasizing here is that spend much time doing the maths of cross multiplying and all that, because you can lose that 1 mark of the final answer if you are not able to do the cross multiplying and all that. So it's very much important that we do that. We talked about the issue of redshift, to say we have redshift when these stars are moving away from our solar system. So when these stars are moving away, when we have a longer wavelength, we now have a longer wavelength means lower frequency, which means now that we are having redshift, which now you must always remember. If we have a higher frequency, it will mean that we are moving towards the blue end. But for grade 12, we said our main focus is on the redshift, which is moving, the stars that are moving away. Hence, we're saying the universe is expanding. So you have seen some of these questions, you will get them in a graph form, like the graph that we were given in that other question that we've done. If I can move to it. That one, we're given the question in a graph form. So we're saying to yourselves that spend some time doing different types of questions. Don't just do the ones that you are given every information on the data. You have seen the first question as well that we have done. We were given the frequency, we were given in percentage, to say we have 7%. We have 7% of the frequency of the source. That is the frequency detected by the listener. So it's very much important to look at different types of questions. You have many question papers that you can continue to revise for this topic, and we are hoping that you will be able to enjoy the topic and continue to do this one. We thank you very much for this lesson, hoping that you will do as many problems as you can. Thank you very much.